Hello everyone and welcome back. Let's continue on with the chapter of dynamics specifically for AS level physics. AS level physics. Now, in our previous lesson, in fact, we had gone through Newton's third law, remember? So let us actually quickly recap that. We had discussed the fact that when it comes to Newton's third law, we basically state that every action force has an equal and opposite reaction force. And from this, we were able to go through some of the properties of the action and reaction force pair, and then we were able to see some examples of how you can deduce the reaction force of some kind of action force. We had done that for the normal force, and then we had even done that for the gravitational force, that is the weight of an object, right? Now, you might remember that when we were introducing Newton's third law, I was talking about a very specific scenario. A scenario where there was a person standing in front of a wall and he was basically throwing a ball towards the wall. And then that ball was bouncing back, right? Now, something that we didn't really mention before, but it's something that's worth wondering about is, where is this force originating from? Now, when you usually think of a gravitational force, a magnetic force, or an electrostatic force, you often know where they're arising from. They're arising from some kind of a field, right? But this is a special kind of contact force where it's only once the ball is in contact with the wall, like so. So what I'm doing right here is just drawing a zoomed in version of the scenario. We had seen last time that it was only upon contact that the ball was able to exert a force on the wall. If you recall, I had described that as the force that the ball exerts on the wall. And then from there, we were able to deduce that there was a reaction force that the wall would exert on the ball. Now, sure, we are familiar with the action-reaction pair of forces, but I wish to explore this action force a bit more. Because if you notice, this force is arising from a collision. So not only is it a contact force, but it's a contact force that's arising from a collision. So now we would like to explore this a bit further. How is it that this force is arising from a collision, and what factors could influence this amount of force, right? So that's going to be our motivation from here on out, okay? So let's pause our recap from here, and actually now let's dive into this exploration of this collision. Now, in order to explore this, you don't have to actually hold up a ball and stand in front of a wall and start conducting different types of collisions. You can do this through a simple thought experiment. For that, let's assume the following. So let's cut off our discussion here, and now let's dive into our thought experiment. So picture yourself in this thought experiment where you're in the comfort of your own thoughts and simply conducting different types of collisions and seeing what outcomes do you expect. Now, suppose you're standing in front of a wall, like so. And in this first scenario, I label it 1. You first throw a tennis ball. That's your tennis ball. Towards the wall so that it collides with the wall. And then you throw a bowling ball. And suppose you throw both of them with the same velocity, let's suppose 5 meters per second. Now, even though they're both thrown with the same velocity, you can guess which one is going to exert a stronger force when it strikes against the wall, right? Take a minute to guess. You must have concluded that it's going to be the bowling ball that exerts a larger force, right? The bowling ball exerts a larger force. And did you notice how you were able to conclude this? You were not really looking at the velocity with which both of these balls strike the wall, because if you think about it, it's the same velocity. Instead, what you compared were their masses. So the reason why you concluded that the bowling ball will exert a larger force than the tennis ball is because the mass of the bowling ball happens to be larger than the mass of the tennis ball. So from this you were able to conclude that the bowling ball is exerting a larger force, and you could also of course invert this argument. You could say that the tennis ball exerts a smaller force because of its smaller mass. This tells you a relation between force and mass. That is, that the force that the ball exerts upon collision happens to be directly proportional with the mass of the object that is colliding. The more massive the object is, the larger the force exerted will be upon collision, and vice versa. So now with this version out of the way, let's look at another version. Now let's look at the same setup. So you're still standing in front of the wall. Let's place you here. The same wall as before. But this time, you're throwing two tennis balls in front of or at the wall. Both of them are tennis balls, meaning this time you're making the velocity, you're keeping their masses the same. But then what's different is that suppose this tennis ball I label A is thrown with a velocity of the same 5 meters per second, but then tennis ball B is thrown with a velocity of, let's say, 50 meters per second. Now clearly one is being shot towards the wall a lot faster than the other. So now I want you to guess, in this version of this thought experiment, which ball do you think will exert a larger force? Take a guess. You must have guessed that it's going to be tennis ball B that will exert a larger force, right? And you'd be correct. The tennis ball B will exert a larger force. And did you notice how you were able to conclude this? This time, notice you didn't really compare their masses because it turns out that both tennis balls have the same mass, they're identical. What is different for both of them is their velocity. And it's precisely this that you were comparing. You realize that the velocity of the tennis ball B is greater than the velocity of tennis ball A, which is why the force that B could be exerting must be larger than whatever force A is exerting. So this tells you that just as how force and mass were directly related with each other in the previous example, much in the same way, force and velocity happen to be directly proportional as well. The faster the object is being thrown towards the wall, the larger the force expected will be. So see how you were able to reach both of these conclusions very easily and quite straightforwardly through just your simple thought experiment. Now, it's these conclusions that will be pretty important to us because now we wish to approach a new quantity from using these two relations. The two relations being that the force exerted during a collision is directly proportional to mass, and the other relation we just determined was that the force exerted due to this collision is directly proportional to the velocity of the object that is colliding. Now these two proportionalities, because they're both directly related, we can use the property of direct relations and combine the two by multiplying m with v and keeping f as it is. So this kind of a combination gives you this. This does work because this one equation basically has both of these previous relations combined together. You can see that the force is directly proportional to mass if you ignore velocity for the moment, and you can also determine from the same relation that force is directly related to velocity by ignoring mass for the moment. So with this combined relation, we realize that, and in fact we conclude quite safely, that the force exerted due to a collision, and it's very important in fact, before I go any further, we should specify what kind of force we're talking about. So what I've been saying out loud, I'll just write it out here. That F is specifically the force exerted during a collision. So this force happens to be directly proportional to this seemingly new quantity that we're calling mass times velocity, right? Now, we haven't really given this quantity a name yet, right? But because this happens to be so important that it's directly related with something like force, we can actually define it the way scientists like Newton had. What they did was they noticed that, okay, mass times velocity, sure, it's not an already existing quantity, but then it's quite interlinked with force. Why not we define it ourselves? Let's make a new quantity that will precisely be mass of the object times its velocity, and we'll give it a new name called momentum. So this is how momentum was first introduced as a physical quantity. It was deliberately defined as the product of mass and velocity. So let us actually write down this definition as straightforwardly as I just described it. That momentum is quite literally the product of mass and velocity. And as straightforward as the definition of momentum is, much in the same way, the formula for momentum is straightforward. You have P, which is momentum, equals mass times velocity. Now, even though it seems like it's a definition that we have deliberately defined, that doesn't mean that we can't give physical significance to this. You can think of, let's say, a ball like so, that has some mass m moving with velocity v. Now we know that velocity is a vector quantity, right? And you can express that velocity vector as an arrow like so, right? So velocity is a vector. Now when you multiply the velocity vector with a scalar like mass, so let's say you take that arrow that I just drew as the velocity vector, multiply it by its mass, you're basically multiplying a scalar with a vector. Now, from basic knowledge of vector multiplication and like the general discussion of vectors, you might remember that whenever you have a vector quantity or any vector for that matter, doesn't have to be a quantity, when you multiply a scalar number to it, so something like, let's say I multiply this by 2, I'm basically increasing its length. I don't really influence its direction because a scalar only has a magnitude, no direction. So the 2 is doing nothing but scaling the vector such that its length or its magnitude changes without changing its direction. But the new resulting vector that you get, in this case 2 times v, it's still a vector. So much in the same way, if we go back to our above scenario, when you have that already existing velocity vector and you multiply it by mass, you're defining a new quantity called momentum, but the physical quantity itself is still a vector because the scalar quantity of mass is merely changing the magnitude of this vector. It's not really changing or influence its direction, right? In the end, you still get a vector. So this goes to show that momentum, like since velocity is a vector, first of all, I'll write it down here. Since velocity is a vector and for momentum, you have a scalar mass multiplying by this vector quantity v. Therefore, momentum is also a vector quantity. So from here on out, we must get comfortable with the fact that momentum, being mass times velocity, is in itself a vector quantity, meaning it's going to have direction as well as magnitude. So let me mention that right here. It has magnitude and direction. And usually the approach we take to give it direction is that when you have momentum directed towards the right, you give it a positive sign, and when it's in the opposite direction, you tend to give it the negative sign. So it would look something like this. So if you have that same object with mass m moving with velocity v to the right, if you compute its momentum, it would be m times v with a positive sign. However, if it were the same object moving in the opposite direction, the convention that we stick to is that when it's towards the left, we give it the negative sign. So it would be m times minus v equals minus mv. So just keep in mind that you might have situations where negative signs occur, and that's merely a change in direction, or the opposite direction to be precise, right? So far, not only were we able to present a motivation as to why we have a quantity like momentum in the first place, we concluded that it's because m times v happens to be a quantity that's directly related to a force that's exerted during a collision. Then from that, we were able to define momentum as the product of mass and velocity, and furthermore conclude that since in this formula you have a scalar multiplied by a vector, and that only scales your vector without changing its direction or its nature, in the end you still get a vector quantity. So we were able to conclude that momentum is a vector quantity. And so we were to take into account direction from here on out, right? Now with all of this out of the way, we're now ready to explore that relation that we ended on, this one. While yes, this relation was there to at least motivate us to figure out, okay, what kind of a quantity should momentum be? It had motivated us to even define a quantity like momentum. We haven't yet explored this further, right? We just stopped at this direct proportionality. So if we do know, so let me in fact write it down, that if we do know that this force exerted due to an object's velocity and mass is directly proportional to its momentum, then what is this relation? It might seem like we're back on square one, not knowing where we can go. Well, in reality, we already have an existing relation for force that we can use to figure out this relation more concretely. You might remember Newton's second law of motion, right? And I'll in fact write it down here. You might remember that according to Newton's second law of motion, we claimed that the resultant force, when a resultant force is exerted on an object, so when it's a non-zero amount, it leads to an acceleration, right? And furthermore, you might remember that we were able to present an equation that could relate this resultant force and acceleration, which is mass times acceleration equals the resultant force. Now, at this stage, this might feel really forced. It might feel as if I'm presenting this relation about force out of nowhere, but it works really well with a scenario like collision, where let's say, or not even collision in fact, let me make this a bit more general. Let's talk about a scenario of just some resultant force acting on an object. When you have, let's say, this object of mass m, let's say it was moving with some initial velocity u. Now when you exert a resultant force, let's say Fr, towards the right, that will definitely cause the object to accelerate, as we already know from Newton's second law. And that acceleration implies a change in velocity. So let me in fact mention that. I repeat, when we mention acceleration, what we mean to say is that there's a change in velocity. And since here in this scenario, we have that the resultant force is acting in the same direction as the object's own motion, we can expect that there would be an additive effect such that, let's suppose the object is speeding up. In which case, you would have of course the same mass of the object, but it's now moving with a new velocity v. Clearly you can, now it's more explicitly seen that there is a change in velocity. And since there's a change in velocity, there's definitely a change in momentum, right? We can clearly see, and let's in fact quantify it. The momentum before, let's call it the initial momentum. By initial momentum, I mean the momentum of the object before the resultant force was applied. That was simply mass times velocity, m times u. The final momentum, which would be the momentum of the object after the force is exerted, that would be m times v. Clearly you can see that the momentum has changed due to this resultant force. So it's perfectly valid for us to use Newton's second law in the first place. So let me mention this here, that a non-zero resultant force has led to a change in momentum. Now do note, it shouldn't be alarming for us that we are stepping away from things like collisions, The collisions were there just to talk about a general kind of process of a force being exerted, simply because I wanted to present this kind of a thought experiment to present like a motivation for momentum. But do remember, now we wish to generalize this further. So instead of just talking about forces exerted during a collision, now we are generalizing it to basically see how the same relation can apply a bit more generally to different kinds of resultant forces. And we're basically moving towards that presentation. So let's go back to Newton's second law, where the resultant force is mass times acceleration. And this time we'll keep in our minds this relation that we've just established. That clearly a non-zero resultant force is definitely leading to a change in momentum, which we've even quantified right here. Now we can work our way into breaking this equation down by recalling, and in fact I'll write it here. Here we'll recall the definition of acceleration, which was it being a change in velocity over some time interval t, remember? I'll write it as delta t. A change in velocity, if you think about it, is nothing but basically the final velocity v minus the initial velocity u. So let me take this expression and plug it into the quantity of a in Newton's second law. In which case I get the resultant force equals mass times v minus u over delta t. Now it's just a matter of me simplifying things further. So I get resultant force equals m v minus u over delta t. Let me open up the bracket in the numerator and I get mv minus mu over delta t. All I did really was just multiply the mass with velocity v and then mass with velocity u. Now let us look at this numerator really carefully, and we notice immediately that this is quite special, right? Notice how you have two important quantities that we've already defined. mv you may remember as the final momentum, as we defined up above. The final momentum being the momentum that the object has after the force is exerted. That's final momentum. And similarly, we have the initial momentum mu over here. So mu is the initial momentum. And just to convince you, you can see it here. Initial momentum is m times u, meaning it's the momentum of the object before the resultant force is exerted. So I can pretty much make these substitutions pretty directly here, that the resultant force is the final momentum minus the initial momentum divided by this time interval. And now in the numerator, you have basically established that a final momentum minus an initial momentum is nothing but a change in momentum. And so you arrive at the glorious result of the resultant force being equal to the change in momentum over an interval of time. And what you've established here is basically a very important and quite a fundamental definition of resultant force. That is that the resultant force Fr is the rate of change of momentum. Now this is extremely important, because in reality, this is how Sir Isaac Newton had even defined resultant force to begin with. And in that regard, you can in fact think of this as basically a rewording or a rearrangement of the true definition of the resultant force. That is, it's the rate of change of momentum, meaning you're basically seeing how momentum is changing with every interval of time. So you can think of it as the change in momentum per unit time. And now here we have very clearly established the true relation between force and momentum. So it's not a simple equivalence, but rather force and momentum are related to each other in that force is the rate of change of momentum. So you're seeing how is momentum changing with each equal interval of time. So here it becomes obvious that as long as there's a change in momentum occurring, there will definitely be some kind of a resultant force involved, right? So how you can figure out how to compute this? You can look at two very simple examples. So suppose we have the first example where let's say you have an object of mass 10 kgs that was moving with a velocity, an initial velocity of, let's say, 5 meters per second. And let's say a resultant force was exerted, and suppose this resultant force was exerted for a time duration of 10 seconds, and then that same object has a final velocity of 25 meters per second. So I repeat, the situation is this, where you have a mass of 10 kgs initially moving with a velocity of 5 meters per second, and then after a resultant force is exerted, it has a new velocity of 25 meters per second, and this time duration during which this change in velocity has occurred is 10 seconds. So the question is, what would the resultant force be? Well, it's just a matter of, so in fact, before I even work this out, I want you to pause this video for a moment and give this question a fair shot, and then we'll discuss it together, right? Starting now. Hope you're done now. Let's discuss this together. So here we have the resultant force being the change in momentum over some time interval. And the change in momentum, as we just established, is the final momentum minus the initial momentum. So I'm just making these relevant substitutions within the equation so that in the end, when I have to plug in the numbers, I can do it quite straightforwardly. Let me solve for the final and initial momentum separately. So the final momentum be the mass times the final velocity, meaning 10 kg times the final velocity of 25 meters per second. That gives me 250 kg meters per second. Now here I'll in fact keep in mind that what I've written here as kg meters per second is precisely the SI unit. So let me just mention it here for the sake of completion, that the SI unit for momentum is kg meters per second. So I'm basically writing that right here, right? So that's my final momentum. Now let me calculate my initial momentum, m times u, 10 times the initial velocity, which was 5 meters per second, and I get 50 kg meters per second. So now it's just a matter of me plugging everything in. So I get 250 minus 50 divided by the time duration of this force exerted, which is 10 seconds, and I get 200 divided by 10 gives me 20 newtons. So for this amount of a change in velocity to occur, the resultant force that's exerted must be 20 newtons. Great. Now let's look at one more example, and just so that we can bring our whole discussion full circle, let's actually bring back the concept of collisions. And I present this example because it's just showing you how fundamental collisions can be in understanding things like force and how it relates to a change in momentum. So look at this scenario. Suppose you have that same object of mass 10 kgs colliding against a wall with the initial velocity of the same 5 meters per second. And suppose after collision, it bounces back with a final velocity of 25 meters per second. Now, and suppose the collision has taken a time duration of just 5 seconds. Now the question is this: we know already from our discussion of Newton's third law that there will definitely be a force that the wall exerts on the ball. Now the question is, let me in fact just call it F. And we know in fact this force F is relevant because it's this force that is responsible for the ball bouncing back. So now the question is, what would this force be? Now because this force is leading to this change in velocity, we can immediately determine that this force can be calculated using the same formula, rate of change of momentum, or the change in momentum over the time interval. Now here too, I want you to give this a fair shot, pause this video, and then we'll discuss our answer. Starting now. You got your answer? Well, now let's compare. So because this is using pretty much the same formula, we'll have the same formula. We can make the relevant substitutions here as well. That a change in momentum is the final momentum minus the initial momentum over the time interval. Now let's figure out the initial momentum, since that's the easiest to compute. The initial momentum would be the mass of the object times its initial velocity, 10 times 5, and I get 50 kg meters per second. But then when I look at the final momentum, I'd wish to just do mass times final velocity, right? But then while I would keep the same value of mass as 10 kgs, the velocity won't just be 25, because while yes, the magnitude is 25, notice that the direction has now flipped. That opposite direction must be catered to by including a negative sign. So instead of me just writing 25, I'll write minus 25. So remember, this negative sign is important here because I need to illustrate the fact that there has been a change in direction. More specifically, a flipping of the direction, because it's now moving in the opposite side or the opposite direction. So with this in mind, I get minus 250 kg meters per second. And now it's just a matter of me plugging everything in. So the resultant force is minus 250 being the final momentum minus the initial momentum 50. Notice how I don't skip the negative sign. I have to maintain it there to illustrate the opposite direction, divided by the time interval of 5 seconds. So this time, instead of the two quantities in the numerator subtracting, it's actually adding, and I get minus 300 divided by 5. And in the end, simplifying gives me minus 60 newtons. Now the negative sign here shouldn't alarm us, because all that tells us is that our resultant force F is being exerted in the opposite direction. And that shouldn't present a problem, because if you think about it, if you look at our diagram, that makes physical sense, because my resultant force, highlighted in orange over here, is acting towards the left, which is precisely the direction where we have been usually associating our negative sign. So all that really tells us is, as it makes physical sense, that the resultant force is being exerted in the opposite direction. Alright? So that concludes our discussion of force in regards with momentum, where in all of this we were able to first present a motivation that could help us define or describe what momentum is as the product of mass and velocity. And then we concluded that momentum is a vector quantity the way velocity is. And then we were able to use Newton's second law of motion to conclude that the resultant force is defined specifically as the rate of change of momentum, or the change in momentum per unit time, where momentum would have an SI unit of kg meters per second, while resultant force would have your regular newtons. And then we were able to discuss two examples or scenarios where you can figure out the resultant force exerted using a discussion of the rate of change of momentum. Alright, now we're very well equipped in understanding what momentum is. In our next class, we'll dive further into some very important properties of momentum, specifically its conservation in closed isolated systems. Alright, we'll meet then. Thank you.